Mente. This is a short introduction to the type of data for the CCS and the San Diego Bay area that are available on the cluster. So first of all, let me log in with the username. So it's going to be SSH minus port 8022 minus X to forward the display, and then it's going to be user-roms at dots.o3d.org. So this should get you into the main cluster here, in the main system here at Georgia Tech. When you log in, I've created for you a directory called SDB data. Okay, in this directory you'll find a whole bunch of files. Let me just start with deleting some files that are generated by these examples so that we can do them together. These are some example of nested configuration. So first, let me say two things. This is the front-end machine to log in at Georgia Tech. However, if you want to do some MATLAB extractions and stuff, I suggest you actually log in on the main node of the cluster that is more powerful than this front-end machine. To do that, we're going to SSH minus X in master. And I'm going to put here the password again that you have in your email. And I'm going to go back to SDB data. Okay, I'm going to fire up MATLAB. And this is the way it's going to work. The first thing that I want to show you are the types of grids that are available. Okay, and so I'm going to describe them in a little bit. So let's start by plotting there are 1, 2, 3, 4. These are 5, 6 grids available. So this is what I define the NEPD, which stands for Northeast Pacific Domain. It's a 10-kilometer resolution grid. Now for this grid I have about 55 years of model simulation from I think the 1950s to 2007 as an output that you could use to provide boundary conditions, and I'll show you also how good this output is in just a while. Now there are other grids available that are higher resolution and more nested. So the second grid is the so-called SCOOS, that stands for Southern California Coastal Ocean Observing System. This is still 10 kilometers, so actually it's the same resolution of the NEPD, so this is probably not very useful. So let's go to the next level. This is a grid that I generated. It's called SCOOS 1, and it's basically 3-kilometer nest that I don't know if you may want to use, but I'm looking at the topography here, and topography doesn't look very inspiring. Perhaps it needs a higher resolution topography for the San Diego Bay. But anyway, this is one of them. There's also a SCOOS 2, which is a 600-meter resolution. But again, I see from the topography that this may not be very good. I have 2 more grids for the California region. I think it's plotting. This is called the Southern California ROMS, SC ROMS, and this has actually a high resolution topography that comes from soundings, so this is perhaps a little bit more useful as a grid. I believe this has a resolution of 1 kilometer. And then the last grid is I have a San Diego ROMS. This is even a zoom very close to San Diego, and this is a 600-meter resolution. So you can see this is a little bit better. Now the issue is that I do have outputs only for the Northeast Pacific domain. So it's the 10-kilometer Northeast Pacific grid, and that's because lately I've been focusing more on climate variability using these ROMS grid. So I really haven't done more simulation at this type of resolution that I would feel comfortable in giving you. They're kind of a bit of a piece of crap, I would say. So anyway, so these are some of the grids. At this point, let me show you the types of output available. I'm gonna open a file here. It's called, I'm actually gonna use an editor here and edit. And this is an EMP file here that shows you how to load various outputs. So let me just go through a little bit. So there are, as I said, for the Northeast Pacific grid, which is the large one, And by the way, before I go any forward, I wanted to show you something. Let's see, this will be Control Z, Control C. In general, if you do a more of plot all grids, there's a function here to load the grids, which is called guarantee grid load, and then you put the name of the grid that you want to load. So for example, suppose you wanted to load the SD-ROMs, the high resolution. You just put it here in quotes. Okay, and once you load the grid, this array GRD has all the grid information. Not only, but it also tells you the absolute path of the grid file in case you want to download it or anything. Okay, and it has the coastline, and this has the high resolution topography as well. So anyway, this is just to give you an idea. So in this case, I have outputs for this grid called NEPD 10. Okay, so I'm going to load it, and I'm going to just plot the topography once again. Okay, oops, this doesn't work, sorry. Let me just plot the topography in a simple way here. Okay. So this particular grid here, for this particular grid here, I have a run that uses the NCEP reanalysis from 1950 to present, and it's forced with climatological surface fluxes of salinity, or fresh water, which have been corrected through a spin-up run, and in other words, is a corrected E minus P climatology such that the model doesn't produce any drifts. And then but the NCEP reanalysis, the winds are kind of coarse, and then for the SST, it also has, aside from the corrected heat fluxes, it also has a time-dependent nudging terms towards the NOAA SST. So this particular run, I have two ensembles of this period, and that's because I start the run with different initial condition to just try to split the deterministic versus the intrinsic. Now, the NCEP winds, as I said, are not maybe particularly great because they're coarse resolution. So there is also an additional output that uses a regional atmospheric model winds. And so here's a list of the outputs. So this is the NEPD 10M, is actually 10 kilometers. This is the period of the output, and so we have 1 and 2 ensemble. Then there's for this same grid, there's one that is slightly coarser, is 20 kilometer. It's the same area. And again, forced by NCEP, there's 3 ensembles. This run is probably not very useful to you. But this one here is still 20 kilometer resolution, so it's not very resolved in space perhaps. But it is forced with the RSM, which stands for Regional Spectral Model Winds. These are high resolution, basically these are downscaled NCEP winds using a regional atmospheric model. And there's these winds has been downscaled from 1950, I believe, all the way to present. And these are part of a project at the ECPC Center, which is the Environmental Climate Prediction Center at Scripps. I think it's, if you go ecpc.ucsd.edu, you'll find out more about it. So this could be useful, or at least the forcing associated with this thing could be useful because the winds are definitely better. They resolve the coastal stuff better. But maybe in the San Diego Bay you have other measurements of winds and so forth. So these are the two outputs, and so how do you load the outputs? So here, this is the list of all the outputs. So we have the NCEP, the NEPD 10 kilometer ensemble 1, the ensemble 2, then the 20 kilometer ensemble 1 through 3, and then we have the 20 kilometer using the RSM winds, ensemble 1 and ensemble 2. So I'm going to give you an example of loading what I think is probably your best option, which is the NEPD 10 kilometer NCEP ensemble number 2. So the way that you load it is there's this function called rout, and you put these strings that I've put here for you, and it loads basically a whole bunch of things. Let me load it and then I'll tell you exactly what it is. Okay, so what it is, basically it loads these things called CTL, CTLF, and GRD. Now GRD is a structured, is a structured array that contains all the grid information, and this is something I find very useful. CTL, on the other hand, is what I call a control map. And what it does, because the output of these models are multiple netcdf files, this is basically a map that puts together all the netcdf files so that you don't have to worry about where the output is and which netcdf, which time record, and so forth. It basically has everything for you. So for example, if you do CTL year, it has all the years and the months. And so for example, in this case, suppose that I want to plot something. Suppose that I want to look at January of 2003, the sea surface height. I can find the record associated with the January of 2003, and I'm just going to paste that there. Let me just put this a little bit further up here. And then I can use this command called rnt load var that loads a variable. You give the CTL the record that you want, in this case the one found in EN, which is going to be record 636. And then it just tells you the variable that you want to load, and it will find the corresponding file that has this particular record that is associated with the Jan 2003 among all the files. And so we can plot, for example, the free surface during that time period. And this is what it looks like. So this is the sea surface height of the model during January of 2003, at least the hindcast. Now these rnt load var routine can also load subsets of the data. So in this case, suppose you want to load the SST, we're going to load from the temperature, which is a three-dimensional array. We're going to load this range of indices in the horizontal. grd.lp is basically the extensions in the I and j direction here, and grd.n is just the surface value. So I'm going to do that, and I can make a plot of the SST, and you can see this is the SST, the corresponding SST. So, and of course here you can load with segp here, you can load any subset that you want. Just put the ranges of indices. Now, how good is this model? Well, we could compare, for example, the sea surface height from this model's output with the San Diego tide gauges. So this is a piece of code that just does that, just to give you a sense. So I'm just going to paste it here. And while this is loading, okay, so this is now the in black the tide gauge of San Diego and the model. And you can see that it's not that bad. It's not perfect, but of course this model is, it's hard to get the sea surface height perfectly. But it's not bad either. I think overall it gets the right type of variability. This is, by the way, it's low past the 6 months, so just to remove the very, very high frequency events. The correlation is actually significant in this case because I was interested myself, but anyway, so let me close it. Now when I did that, I also made use of this other routine, for example rnt extract time series, which allows you to extract a time series in a given longitudinal and latitudinal range, and for a given klev, which is a level. But anyway, these are extracting routine. What else? We could also compare, for example, the salinity of cal coffee in the California current region with the one from the model, just as a different measure of scale. And let's see how it looks like. I'm just curious. Well, I looked it up before. It's not too bad. Let's see. It takes a little bit more time now to load because the salinity, of course, you're loading a lot of data. Okay, very good. So you can see that, even here, especially in this last period, it does pretty well. It captures some low frequency. And this is a kind of a very quick and dirty comparison. But actually, the NEPD run, the one at 20 kilometer, for example, has been used in a study that I published just recently that actually captures salinity very well. I'm just going to show you real quick on the web. Let me just put my web browser here so that you can see it. So I'm going to go to my web page, imanu.org, and there's a study that we published just recently. It's called this one, the North Pacific Gyre Oscillation Links Ocean Climate and Ecosystem Change. And if you look at the PDF, which is now loading, let's see. This is a comparison here between, for example, the model sea surface salinity. This is a very more accurate comparison in the Cal coffee area, and you can see that the model actually does very well with compared to the coffee, the correlation is 0.6. So actually these models are not that bad, and this paper was about some kind of an large-scale climate pattern that I call the NPGO, and this is a comparison between the NPGO index and salinity to show that it's pretty good, but that's not something you're probably interested in. But one thing that I wanted to point out on the website, that here I'm making use of these R&T tools, which which is a toolbox that I make use to make all these plots. And here on this web page there is a ROM's tutorial page, and it gives you an overview of some of these things that I showed you, like for example the CTL array, what it is. And these are movies similar to this one that I'm making right now that show how you can use and create these CTL and so forth. There's also movies about 2D mapping, 3D mapping. This is objective mapping, creating forcing, and so forth. But I'm going to stop here for now, and I will produce now another video that explains how you can use some of these toolboxes to actually extract the data from one of these output and place it on any other grid that you want, because eventually you want to maybe run a nested grid. And so I'm going to, in the next video that I'm going to send you, I'm going to just discuss this idea of 3D mapping nesting using the R&T toolbox. Okay, thank you.